This is the okay, pardon. Some asymptotic stability problem in a traffic flow model that will. Sorry, I think you can see that. So this is a joint work with Tej and Nader. And what I'm going to do is to try to explain. I will not go into the full mathematical details of the proof. I want to give an overview, which will be easier to understand. Okay. So the model I'm going to take is the model of traffic flow on an infinite highway, which will be defined by the real line R. So the position X is life, and my highway is infinite, no entrance, no exit. I will consider two quantities. First, rho, which will be the density of car at any point. It's between 0 and 1, 0 being no cars at this point, 1 being you're saturated, you have no more rooms to put cars at this point. And U will be the speed, the average speed of cars at this position. And so you have two unknowns, so you need two equations to describe their development in time, like how they move in time. And this is so the model I will take for that is called the IRZ model for O, Haskell, and Zhang. And it's two equations, one on rho, one on U. The first one on rho is the one I fully written here. It's telling you that the mass is moving with time at the speed u and is conserved. The fact that the dt rho is the derivative with respect to x to something means that the mass is conserved. In some sense, you have no entrance, no exit on your highway, so car does not disappear. Your density has to be the same. And also that they move at speed u. The second equation is how your speed will change with time. I mean, the first one is just cars move at their speed and doesn't disappear, fine. The second is how your speed change with time. And for that, you have several things to consider, because it's not just because there are people in cars taking decisions and you want to model the decision they are going to take. And for that, we will have three effects we consider here in this model. So the first one is just the part I wrote here. Left some part in blank for now, but just dcu plus u dxu is equal to 0. This is the fact that the speed moves with the car, meaning that the speed is not connected to a point in the road, but to the cars at this point. So if the cars move, the speed of the car moves with it. That's simply this term here. We add a second term, a term of relaxation here. So 1 over tau, tau is a constant, it's a characteristic speed. And what you see is that if you forget about the u dxu in the middle, this tells you that dtu is equal to 1 over tau times something, depending on u, linear u. Meaning that the speed wants to converge at least exponentially fast, the time characteristic time being 2. You want to converge to u of rho. So u of rho is the speed you want to go naturally. Rho de rho is uf times 1 minus rho. So if there are no 1, rho equal to 0, if you're alone on the highway, you want to go at speed uf, which is kind of the limit speed you can go on a highway. But if there are more cars than none on the highway, they start to get some number of cars in front of you. Well, maybe you are not comfortable going at full speed on this part of the highway. And so this is modeled by this function u of rho, which decreases when rho increases. So if there are some cars in front of you, you might want to go at the lower speed than if there are no cars in front of you. So this is this term. And finally, the third term we add is pressure effect. So it's the function h of rho, which is here. And what does that mean? Putting it both here and here is that what is transported is not the speed. It's not transported by the flow. What is transported is the speed plus this pressure. And this pressure is something that is always, derivative is always strictly positive. And what adding this term does is an instantaneous effect of slowing down or going faster if there are more or less cars in front of you. So if there are more cars in front of you and you're going into it, you're going to slow down because there are more cars in front of you and you want to be sure that there is no issue. So this term will do that. If there are too much car in front of you than before, it will instantaneously slow you down here. If you're more familiar with the gas cinetic or things like that, I call it the pressure because it's exactly the pressure. There are more people in front of you, they will push you back in some sense. So, yeah.
So because this relaxation effect, the Actually, what you want to achieve is sort of ideal speed of the vacuum. When there
yes.
are cars.
I mean, what you want to do is that if
so
there are
density equals 0.
yes, but I mean, the speed you want to reach is not the speed of the vacuum, it's a speed depending on pressure, average pressure if you want. So we'll see, basically this guy will tell you what speed you want to go if the density is constant, for instance. And in fact, it's exactly my next thing, is that this equation has a particular solution, which is very simple, it's a constant. You take rho 0, a constant density, and everyone going to the speed u of rho 0, which is exactly to cancel the term here. So meaning, your highway has the same density everywhere, and everyone is going to the same speed. And it turns out that it's also the speed they want to go to, because of the density. So it's a constant solution. You just plug it in and you see that it's a constant. And the question we are interested in.
The condition h prime of 1 minus equal plus.
Ah, yeah. Yes. So I have h prime of 1 minus to be plus infinity. It's a way to force rho to be less than 1 at all time. Like the density is between 0 and 1, 1 being you are saturated. And the way mathematically to force your equation, force rho to never go above 1, is to impose the h prime to be plus infinity at 1. Meaning that if the density in front of you is almost 1, and you're going to go in and make it above 1, this pressure will completely prevent you to do that. That's the point. I mean, it's, yeah.
Why are the
for 0 plus? Because it depends on the physical model. Some people take 0 plus being plus infinity as well. You're not forced to. I mean, what we will do here is avoid the vacuum because it's weird. But yeah, you might save it. Okay, so now that we have this constant solution, what we want to understand is the stability of it. Meaning, if you have a nice constant flow of cars and you have someone that breaks down at some point, does it create a big perturbation? It creates initially a small perturbation. Does it become big or not, and why? So the first thing we are going to look at is what we call the linear problem for it. Meaning, you take your equation here and you plot instead of rho, you plot rho 0 plus rho, where rho will now be a small error and rho 0 your main profile. You plot it inside of it, you have a lot of terms, and you take only the first order, meaning the term depending only on rho and u, like the small perturbation. You have non-linear term, rho square, u square, and stuff like that, but you forgot for now. So you get this equation. So it's a system, of course, because you start from a system. And you see that rho and u is should be small. It's a perturbation of rho 0, u of rho 0, which is your constant solution. And it's a linear problem. You see it's what is dependent on rho and u only linearly because you've just removed all the non-linear terms. So this linear problem is explicitly solvable if you use Fourier, Fourier variables. Because if you take the Fourier of this operator here, you see this is, if I call this matrix A, this matrix B, it's the matrix A times I psi plus B. And so it's the derivative of your function plus some fixed matrix independent of time of your function equals 0. So it's exponential minus the matrix time t. And that's completely explicit, everything. You can compute as well the eigenvalue of this operator in Fourier, which I call lambda plus or minus of psi, because not psi is your frequency. And what you want for the stability is for the real part of this eigenvalue to be positive, because your solution will be exponential minus your matrix T. So you want the eigenvalue to have a positive real part. And this is not true in general, but it's true under this condition here. Under the condition, which is not always true, it's h prime of rho 0 minus uf being strictly positive. So h prime is connected to the pressure. Uf is the free speed, the speed on the vacuum. It's just uf because here the u of rho is linear. So basically, in fact, it's the derivative of u of r. So this is why you see uf. And so this gives you a criteria telling you that you look at your constant thing, you compute h prime of rho 0. If it's bigger than uf, then you are stable. If it's less than uf, you can show that you're unstable. You can show that the real part of the eigenvalue, one of them is negative. Okay, so this is the linear stability in Fourier. Everything looks good. So this criteria how can you think of that is that you can think of it this way. So you have two effects, the pressure and the relaxation. You want to go to a particular speed. The fact that this is strictly positive means that the pressure is winning on the relaxation term. What the pressure wants to do is to prevent you to go in a direction. If there are more cars in front of you, it wants to prevent you to go in it. So it will prevent you to create shocks, for instance, which would make the derivative explode, for instance. So, and the linear problem to be unstable because you converge to shocks. And so H' is an ally to prevent shocks, and UF is not. And the contrary, in fact, UF makes you that if you're almost at a shock, because you want to go to some particular speed, maybe you will go faster and start to create the shock. H' prevents you to do that. The two effects are of the same order, and so you need to see which one is winning on the other, and it's exactly the quantity which is here. So that's all good, that looks good. The issue is that this is only the linear problem. This is not the stability of your true problem. You've neglected a lot of terms that you expect to be small, but I mean, you have to prove that rigorously. And if you do Fourier method, all the nonlinear terms, when you take the Fourier transform of the nonlinear term, are a pure mess, because it's nonlinear term. If you take the Fourier transform, you have convolution, nothing go your way. And so we are going to look at the linear problem in another way. I mean, we have that in mind that this criteria appears and everything should work in that case. But if we want to do the non-linear stability, meaning we don't forget any error term, we have to do the proof differently, because in Fourier, it's not well adapted to the non-linear problem. So to do so, instead of considering rho and u, your two variables, you just shift them in time. You add lambda star of t for some lambda star that I didn't wrote here, but I should have. It's something very something explicit. It's u of rho 0 plus rho 0 uf, if I remember correctly, minus rho 0 uf. And so q and v, sorry, are the same variable rho and u, except that you have shifted them. And if you do that, the problem is very nice, start to be very nice. And you can, instead of having a system of two equations coupled, you can decouple the system and get, for instance, on Q, you can do the same on V, but on Q, you will get an equation simply on Q, not on the other variable. So it becomes, instead of being a system, it becomes a one equation thing. Of course, instead of being of order one, meaning only one derivative in time in X, you have second derivative everywhere. I mean, on these three terms here, but not on the last one. And now you see the condition H' of rho 0 minus UF appears here. And you need this guy to be positive so that lambda 2 0, which is one of the constants appearing here, become negative. Why is that? Because you see that in front of the second derivative in X of your function, you have lambda 1, lambda 2. Lambda 1 is always positive, and lambda 2 can change sign. But if you look just at the last two terms, you have derivative in time plus this guy, second derivative in Q. And this, if the coefficient in front of it is negative, then this is the heat equation and you have decay. And if it's positive, it's a mess. It's not the heat equation. And it higher frequencies start to grow very, very, very fast.
When you say heat equation, you are thinking about terms.
The last two. I'm thinking about the last two terms. If I forget everything else, I have the last two terms, I have a heat equation. That's, and if I don't, well, it's more complicated.
Just one remark, your lambda 0, 1 and lambda 1, 0 is the same.
Sorry?
Sometimes it's up, sometimes it's
yes.
So the other thing maybe that's the relation with lambda plus and minus.
The thing is that lambda plus and minus depend on psi. I think, if I'm correct, lambda 2, 0, like lambda minus of psi when psi is small, look like some constant on psi square, and the constant is lambda 2, 0, or something like that. I have to, there is some relation.
Yeah, it's related to the psi small.
Yes, it's related to the psi small. Yes. So this equation here, as I said, if the coefficient here is negative, you see the heat equation here. And if you forget about this term and you look at the first three terms, this is the wave equation with two speed, lambda 1 and lambda 2. And so you have two effects. You have kind of a wave equation and kind of a heat equation. And it turns out but if you're motivated, you can show that this equation has an explicit solution. You can write explicitly what is the value of Q. And I'm sorry for the next slide, but this is the explicit solution. If you have this equation, I add a source term S and some initial condition, then here is the formula to compute the solution explicitly. It's a sum of all these terms. So it's a mess. There's a lot of terms. There is a function V that appears everywhere, which has a horrible expression. It's a mess. But if you forget about it, what this equation tells you is something very nice. It tells you that you have the best of both worlds in this equation. Meaning the first world being the heat equation, meaning that things will decrease like 1 over square root of t. And the second is the wave equation, which has finite speed of propagation. Meaning if you look at something at what point, you can create a light cone, and it can only depend on what happens in the light cone. There's a finite speed of propagation. And here there's the heat equation that makes things decay. And this horrible formula tells you that both happen at the same time. They work together, they continue to work both. And it gives you this way to computing your error at some time t. So what I'm going to explain here on this graph is exactly what you can do rigorously on this formula here, but it's easier to explain on a graph. So what is this graph? Here is x, here is time, here is x. So this is your highway. And this is your highway evolving in time. Like when you go up, you increase the time. So this is how your highway evolves. If we can do drawing in the third direction, what I will put here is the size of the error. For instance, if I put something like this, that means that there's some error term here, meaning my initial perturbation is here. I can put it here and so on. And what I want to understand is how my perturbation evolved with time, meaning when I go up. And so the question is, if I give myself some x and some t, meaning some position on my highway and some times t, I want to understand rho of xt being my perturbation at this point and at this time. It will depend on the initial perturbation, meaning the perturbation on this line here, which is what happened at time 0. And I want to understand how does it depend on this perturbation. And what I said, that you have the best of both worlds, is what is done on my drawing. The first thing is you have a light cone, meaning these two nice straight lines here. You see it's x plus some constant times t. Here it's x plus some constant times t. And it tells you that the perturbation here only depends on the initial perturbation on this part between the two wave points. If your initial perturbation was, for instance, completely supported here, well, at this point, it will be 0. There will be no perturbation. You have a finite speed of propagation. Perturbation can only come from the light cone here. So this is the part of the wave equation telling you that you have to, your perturbation cannot go very fast. You have a finite speed, which are explicit. And the second thing, which is the heat equation, is that in fact, it's not like an average of the perturbation here. In fact, okay, you can only see that, but the true value of what happened here does not depend uniformly on what happened on this part here. It's mainly concentrating around one specific point. Meaning, you have this line, this dotted line here, which is the speed lambda star, so the speed of your perturbation. And what it tells you is that if you want to compute what happened here, you don't have to look at the full light cone, you just have to look at this particular value here, and you take an average of what happened around here, on something of size square root of t. This square root of t is coming from the heat equation. So that means that, okay, your function can depend on what happened here, but it will take the error here, and it will be exponentially small compared to it. It will be like an average of what happened here, times an exponentially small things in time. And what happened here, at this size square root of t, it will be of size 1 over square root of t times the average of what happened here. So this is the best of both worlds. You cannot depend on the perturbation if you're too far, and even if you're not too far, you can only depend really on the perturbation near something of size square root of t, which is a lot smaller than t, the size of the cone. And this is the main part, the part of size square root of t around one specific point. And everything else, it exists, but it's exponentially small in time. But this part is in 1 over square root of t. Mathematically, it's written like this, telling you that your function u and rho, the x minus lambda star t, meaning you follow the dotted line. This is exactly the dotted line. And the size of the perturbation here can be controlled by two terms. One, which is, you see, k over 1 plus t power 1/2, so 1 over square root of t times some average of your perturbation. And you see that you have an exponential minus something, and the something is y squared over 1 plus t. So if y is small, if y squared is small compared to t, this is 1. So you see an average of your perturbation. But as soon as y squared is of size t, meaning your y is of size square root of t, so the size exactly of the square root of t, which is here, then the coefficient here is exponentially small, and you don't see anything. You have another error term, but it's itself exponentially small, so exponentially minus dnt. So this is there is also an exponentially small part that I've not talked about, but anyway. So what are the good things about these results is that you keep some information on where the perturbation is localized, meaning it follows some particular speed and it's spread like square root of t, which is much better than if you just know the light cone, because the light cone will say perturbation here will develop like something of size t after time t, but here you have something of size square root of t, mainly. So you gain something. Unfortunately, we cannot compute the first order. So you see that this is a bound, this is less than something. I have no proof that the true, if you try to do reverse side to show that it's bigger than something of size 1 over square root of t, it's complicated. In fact, there are cases where we think that your size 1 over t, for instance, you have some gain, but it's not in calculation. And finally, the perturbation mixed slowly. This is the idea that they spread like square root of t instead of just the light cone, which will give you size t. Okay, so this is nice. Now, how do you show that everything I just said is still true? Because here everything was linear, so we forgot about a lot of smaller error terms. But if you plotted them back, what happens? And in fact, so what happens is that you can still do the same thing of writing your equation. So on V, you still write the same equation, so the wave equation, the heat equation, but now things are more complicated. Why? Because now your two values, lambda 1 and lambda 2, before they were 0, because they were constant, but now lambda 1 and lambda 2 are no longer constant. I mean, you're non-linear, so they don't depend on they depend on V, and in fact, they depend also on Q, on the other term. And you have a new term at the right. The omega 1 will be small, but you have another term at the right. And so, first of all, you don't have an explicit solution anymore, because lambda 1 and lambda 2 are non-constant, so you don't have explicit solution. Exactly as I said, lambda 1, lambda 2 no longer constant, so this makes things very complicated. You have an additional term which will count for a lot in some sense, but with a small coefficient in front of it. And what you want to do in this kind of case, things you can try to do, is to do a change of variable. You change coordinate, you follow characteristics or things like that, to make some of the coefficients being constant, which would be cool because then you go back to the linear case. Unfortunately, you see that you have three coefficients you want to make constant: lambda 1, lambda 2, and omega 1, that you want to make equal to 0. But since it's you can only make two of them constant at the same time, not the three at the same time. This is because you can do a change variable on the position and the time. This gives you two ways of considering things, but you need three ways of considering things to keep the three terms. So you cannot go back to the linear case like the nice characteristic things or stuff like that. And the second difficulty is that, as we said, the perturbation is of size 1 over square root of t, which is very slow. It doesn't go to 0 exponentially fast. And so when you look at nonlinear problems, this is kind of slow, and maybe the term we forgot make it go back. And so maybe you couldn't, in fact, neglect that. And I will skip that because I don't have time. And let me instead do things on the graph. What I want to say is that we can do it in the nonlinear case, but it's a little more complicated. So what happened? This is the same graph as before. So this is your highway in time. This is highway at 0, highway at t. You want to compute the perturbation here. In the linear case, since everything were constant, what would it mean? It would mean that the two line here was nice straight line for your light cone. But since your lambda 1 and lambda 2 are not constant, your light cone is these two blue lines. which are not constant anymore because they depend on the perturbation. They are almost constant, they are almost straight line, but there are some perturbation. And in fact, they can go a little further or a little less further. They don't have necessarily the same endpoint than your linear line cone. And they are non-linear, meaning that if you instead this point here, you took a point here, it will not be the same two curves translated. You will take different shape depending on position. It's a mess. The second difficulty is that this nice straight line here as well, which was the third one, is no longer a straight line as well. You have some perturbations. It's a nice, it's not nice, sorry, green line that does not necessarily hit at the same point. So instead of having everything which is nice straight line, you have this weirdly curved line, and the curves depend on the position, depend on the time, depend on the function itself, but it's a mess. But what we can show, and this is the slide that I skip, is that, okay, maybe the line cone is not straight lines, but I can take a line cone which is a little bigger than the linear problem. So this line here, I can take them just a little bigger to be sure that this blue line is included inside of it. And so if I take this bigger line cone to be the one I use for the estimates, it will be fine because I will not have forgot everything. I will not have forgot anything, sorry. I will be something that includes all the case I can see. But I have to take it a little bigger than the linear case. The second thing is that, okay, maybe this green line no longer follows this nice straight line, but it missed it by something. And we can compute that it missed it by something of size square root of t at most. But that was okay because in this area, we just said that around this point of something of size square root of t, here things are almost all the same. We take an average here in the vicinity of size square root of t. So if this point was not here but moved by a distance square root of t, in some sense, it's still the same equation. You just change some constant in the problem. And so what we can show by a bootstrap argument is that you can do exactly this estimate. So this is what I wrote here. It's maybe a little complicated. So yeah, let me just go back on that and then I will finish. So what we said for the linear problem, which is here, is that your function can be estimated by two terms, f and g. G is something exponentially small, and f is something of size 1 over square root of t times some average on something. And for the nonlinear problem, we can do the same thing, except you see that the speed are no longer lambda 1, 0 and lambda 2, 0, which are the size of your line cone, but you have to add plus delta in one sense and minus delta in the other, where delta is something small but not 0. That means that your line cone, instead of saying I can only see what is here, I say I can only see what is here, with a small difference, and that's fine. The second thing is that the coefficient here, the a, which is here, so it's kind of a size around square root of t, like when I say here, you see something that says square root of t, there is a characteristic distance, some a. Well, the a for the nonlinear problem is less than the a for the nonlinear problem. Meaning for the nonlinear problem, maybe you have to consider something of size 2 times square root of t instead of 1 square root of t. But I mean, that's still the same when t is large, when time is large, it's still the same thing. So just I will summarize here and then I will stop because yeah, it's time. So what you can say is that for both a linear and a nonlinear problem, the stability has some speed. The lambda star, which is u de rho 0 minus uf, which is the speed of the dotted line here, telling you that if your perturbation is big here, after times t, it will be big here following this dotted line up to something of size square root of t. So this is we spray like the heat equation, so like 1 over square root of t. And this is not obvious because it's a wave equation. So things could have spread like like t, but instead you do it like square root of t. At least it's a bounce. It's not faster than that. Maybe it's at least not slower. Should I have written? Like it's at least like 1 over square root of t. Maybe it's better in some cases. And yeah, this is not important to tell you that your perturbation, you don't have to take a nice blob at some point. If you take two blobs at two different points very far or n blobs very far from each other, if they are all small, everything holds as well. And UDK like 1 over square root of t, if you just want to do a bound, so if you want to know how fast you go back to your constant state, it's like 1 over square root of t. And I will stop here, I will not talk about the rest. Thank you for your attention.
One that you're showing.
Yeah.
So what it says is the density at point x and t is influenced by something which is ahead of it and which is behind it. So information is moving both forward and back.
Yes.
But traffic is an asymmetric system, totally asymmetric system. And to my knowledge, information generally, I mean, any perturbation moves backward.
Yes.
In some cases, it moves forward, but both will not happen together. So what does this mean when you're drawing this flow?
Okay. So what this triangle means is that that information at this point can depend on the information of everything, on both sides.
Yeah, but it is coming from your equation, right?
Yes.
So is it an artifact of the way you model it, or have you not taken into effect the asymmetry? Because both should not happen together. That's what I maybe say incorrect.
Think of it this way. So the one that's sloping backwards, that's possible information coming from a cube that's moving quickly. Yeah. The one that's sloping this way is possible information that's coming from free flow that's coming into.
Yeah, but do both happen to meet at some point? Because
they could. Because you're looking at what could have happened in the past to lead to what I'm seeing next to. That's the question. It's information is still populating. It's things are only affected by what's happening. But when you look at it this way, you're trying to say, well, at some point in the next t, what could have affected in the past that you have. So that's the way to think of where's information propagating from, not how a car is propagating.
Yeah, I'm looking at information propagation, but we have this. So the kinematic waves can be either positive or negative. It cannot be both, right?
Yeah, but we can have positive on one side, negative on another.
Yeah, this is a bound in some sense. This is at worst, this can happen. It's not in average or at best. At worst, it can depend on everything here.
Does that correspond exactly to those lambda 1, 0, lambda 2, 0? I'm not sure it corresponds, but when you said that, usually you think about it as make low going
into the downstream.
Right.
So if you have low density, like traffic, then the information propagates into the downstream, the direction of traffic. If you have high density, then information propagates in the opposite direction. There are two finite speeds, so UF in this case would be the fastest of things to propagate in the direction of traffic. Well, and there's also the derivative, again, in this case, there's also a finite speed things that can propagate.
Yeah. So just to go this way, what I'm saying is that you see this idea of like either is going forward or backward depending on the density is connected to the value of lambda star. The speed, lambda star is like the kind of main speed your perturbation will take. It will propagate a little, both on this one, but it has a main speed, which is lambda star. And if you don't follow it, your perturbation becomes very small, very fast. And this speed is, here you see that it's going this way, so it's going faster than the flow, because I've taken here a case where you have a low density. If you took a large density, the lambda star will become on the other side, and this dotted line will be this way. So yeah, so what I'm saying in that sense, I think we're saying the same thing, is that perturbation has a direction, but what I'm saying is that the main part of the perturbation has some direction, but there can be some small error that goes in the other direction, for instance. but it will be exponentially small, whereas this part is not exponentially small.
Just a question about UF1 minus rho.
Yeah.
So how sensitive is your analysis to that? Different rotations, it's still go?
Yes, it still go. What will change is that the SCC only shows that I don't do it, but I'm 99% sure, because this guy will be H prime of rho 0 plus U prime of rho 0. Since U of rho is UF1 minus rho, its derivative with respect to rho is minus UF. So this guy would be minus UF. And you need this thing to be strictly positive. But if instead you put a general relation for U of rho, just replace by U prime of rho, and it's strictly positive. Pretty sure that any relation of rho.
Is it clear for you have H that exists or 0?
That's a good question. Usually, what happens is this graph. So this is H prime of rho, and the graph looks like something like this. This is one. And usually, you have the constant here. So you have, if you are low density or high density, you're stable, and then you're unstable. But the value of UF and H prime depend on what people are doing in the highway, things like that. It depends on, I mean, it's kind of experimental value depending on the highway, how people react, and stuff like that.
So let's say the set of the zero to satisfy this condition is from point like or like intervals.
It can be intervals, like depends on what model you take. One thing also is that
like non-connected intervals.
Yes, it might happen. Like in some sense, I don't care. My answer.
No, I was thinking from the physical point of view, what it means to have.
From the physical point of view, this is usually what they suppose. This one. Yeah, case where your pressure doing things like that are.
For example, just when the density is low or when the density is high.
Usually, yes. Usually, yes. After that.
Sorry, I have a question. Now, in the unstable case, right? In the unstable case, so it's either the low density or the high density. So in both cases, normally we have some instability formula. Can we analyze it? Like how to understand what's happening in these cases? Is it the same thing happening or different? Yeah, just the physical picture.
I guess it's the instability in the traffic engine would be that the Q keeps building up. So we're not. We're not talking about.
It's just a guess that the two things could be different. The physics of the two things could be different.
The instability is in the middle part, not the two extreme. Middle part is the stable part.
No, yeah. Yeah, but okay. But I mean, if you are close to me or close to me, it's different, right?
In terms of pure mathematical thing, if you look at the linear problem in Fourier, the instability means that the high frequencies start to grow exponentially fast at the linear level. The low frequencies are fine, but the high frequencies start to grow exponentially fast. So you expect a shock as the first thing that happens. It's complicated, it depends on the non-linear term. I don't think that answers your question.
Stability is here measuring how far you are from some equilibrium state. for us, we care about some equilibrium, some equilibrium instabilities, and other equilibria to be good. So we want the things to tend towards diagonal traffic. So in that case, even if you have stability at very high density, for us, that's creating instability in traffic. What happens to the overall picture is you're going to get huge instability, even if it is stable.
Yeah.
I guess, so just a guess, if you start to smooth actuation like this, after some time, you create a shock at some point, and then after that, the density will start to get constant equal to the value of the high part of the shock. Exactly what the situation. That we will in time, you will look like this.
And that's in the, if you are close to.
Well, if you are.
Okay.
And the thing that the size of the shock is dependent on the difference.
Okay, so then you are going to, so you will approach the higher, you will approach the higher, you will approach the higher density, right? You will go to something which is higher density but stable.
Yes, on the left side, basically. So you start with the average rho 0, rho 0, rho 0, and then here what happens in long time is that you have a point where you go from rho 0 to rho 0 6, 7. So you have a slowed down thing on the other side of that equation. And so this is completely unstable. But
but then you go, you will build up till you reach rho 0 plus epsilon.
Yes, you build up from your shock. It's a yes, I agree for that.
So your analysis is also the case when the Fourier values have the real part equals 0.
So what happens if you look in Fourier, real part equals 0 can only happen only at frequency 0. And that's it. After that, if you're in the case where the SCC is strictly positive, the two eigenvalues are always positive. Just that one of them converges to 0 at psi equal to 0. And this is what yes. Yes. And basically what you have is that lambda, I think, is the plus of psi. For small psi, is like SCC of O0 times psi squared. So first of all, this equation, because the low frequency are like psi squared, this is the fifth equation. This is the worst part because once you're far from psi equal 0, both eigenvalues are strictly positive if something is above the psi. You have exponentially fast decay. Then for low frequency, you see the heat equation, and this is the equation, the heat equation. So when this is 0 negative,
so you never encountered the case of the purely imaginary values.
No, except psi equal 0. But they are both. You can show that one is always the one that cancels is always strictly increasing, and the one that never cancels is always decreasing, but converges to constant strictly positive. So, on top of the
By the way, just to mention, you're always working in something similar to this, but over graphs. I don't know if you have considered that case, because it helps you to model the structure of the the different paths that you might have. So he's studying how the density propagates over the graph.
Yeah.
So you might have like several constraints. I don't know if it could be useful. Just for you to know what they are doing.
Yeah, there are thing we are doing right now is just the traveling wave, which is this guy. It's going to thing. Is this thing stable? Yes, no, why?
I see.
The answer is yes, but it's complicated. Okay.
Because they want to compare afterwards different topologies over the graph, so you can sort of get an idea of what graph or what direction is optimal, or could guarantee some stability properties in front of other architectures.
Yeah.
This makes just one comment. This makes a lot of sense. I mean, it's the idea that you have more instability in the middle, right? Because what that corresponds to is more heterogeneity, right? If you're free flow, there's very little interaction between the parts. Heavy congestion, you have deterministic interactions. You can really have to be very limited in what you can do with respect to a traffic jam. Whereas what happens in the middle is you get that heterogeneity and you start to see. So this makes sense with your. Yeah. That's maybe another way to interpret this.
The other thing I think which makes sense is that when H prime start to be large, things get more and more stable. because when H prime is large, that means that people are very aware that if there are more people in front of them, they don't want to go inside this jam. They want to keep away from it. And this makes a lot of sense. If you have a jam somewhere, even if you're far from it, if you go inside of it, you will break and the jam will continue because of you. But if you slow down before and the jam disappears before you go inside of it, there is no longer any jam. And this is H prime. The higher H prime is, the more careful you are in the fact that if there are more people, you will slow down not to create a jam.
So if we can control H prime, another benefit of this is you get less stop and go.
Yeah.
And let's say it's emissions has implications for emissions and all sorts of things. So they call this eco control H.
Yeah. H prime is like how people react.
You want to ask if there's any question online?
Yes, can you check is there any question online?
Okay.